Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosine River College in Sacramento, California. This video is another video in the series on sum indifference identities for trigonometry. You should have already watched the video on the derivation of the theorem for sum indifference identities for sine and cosine and tangent, and watched the video on how to evaluate trigonometric functions involving non-special angles. In this video, we're going to actually use the whole breadth of the sum indifference identities for a bunch of different styles of problems you typically see in a trig course. So the first one is just using an expression, asking you to rewrite an expression as a single expression. Notice this expression is actually just a difference of a product of cosines and a product of sines. This requires you to have some experience recognizing that this cos minus sine is actually a sum or difference of angle identity. And because you're new to it, I'm just going to show you it right here. Cos minus sine is the cosine of first angle plus second angle. So it is going to be the cosine of a sum of angles. I'm going to erase that so I can come back to that later. But I rewrote it right here. So cosine of alpha cosine beta minus sine alpha sine beta can be rewritten as the cosine of the first angle plus the second angle. This is cosine of 5x. Very, very nice compressed version of what they handed us, cosine of 5x. That's just what that function is. And this gets used quite often, so don't sell this short. It is actually a very powerful theorem. Then you're facing what I would call a combination of functions. It's sine of 8x cosine of 3x minus sine of 3x cosine of 8x. And we're asked to graph that function. And if you did not know the sum and difference formulas or the sum and difference identities, you'd be stuck. You wouldn't be able to graph this by hand. However, there is a sum identity or a difference identity specifically. Sine of alpha minus beta is sine alpha cos beta minus sine beta cos alpha. Remember that cosine of a sum or a difference, it goes cos sine sine. The sine of a sum or difference each term involves sine and cosine. So when I see two terms, which I see right here that is, and they both involve sines and cosines, then I know it's likely a sum or a difference formula for the sine. And it looks to me like playing the role of alpha is 8x and playing the role of beta is 3x. And you could see alpha, and going over here and selecting a different highlighter, beta and beta. There we go. So let's go ahead and rewrite f of x. F of x is going to be equal to the sine of alpha minus beta, because it's a minus sign. Sine keeps the sign. And that'll be the sine of 5x. And we were asked to graph this, so let's go ahead and just graph it. Its amplitude is the absolute value of its coefficient, which is 1. Its period is 2 pi over the coefficient of x, which is 5. The step size is the period divided by 4. It just allows us to plot points easily for graphing. So that's 2 pi divided by 5, and this is all over 4. So that's going to be pi over 10. That's what that reduces down to. The phase shift, well, you'd have a phase shift if there was a plus an addition or a subtraction on the inside of the sine function. Basically, if you had a addition or subtraction within the argument, but there isn't, so it's 0. And the vertical shift is also 0 because there's not a plus number on the outside or something like that. So with all that being said, let's go ahead and graph this. I'm just grabbing my ruler here and dragging it down terribly slowly. I can take the ruler out for now. It is a positive sine function, so I'll just go ahead and maybe I'll even plot the points. So let's say that that's the beginning and that's the end, halfway through, and then here and here. I'll go ahead and just try my best. That's a pretty decent sine curve, I guess. We started, since there's no phase shift, we start at 0. Step size is pi over 10. So this is 2 pi over 10. This is 3 pi over 10. If this does not make sense to you, please see my video on graphing sines and cosines. But there you go. That's one full period of, or one full cycle, if you will, of the sine function that we're being tasked to graph. Let's go ahead and draw in the y-axis right there. Whoops. And right there. I'll turn that off now. So there's my y-axis. And the maximum occurs at the amplitude of 1, and the minimum occurs at the depth of -1. And it's 1 and -1 because you don't have a vertical shift and the amplitude is 1, so there you have it. And it continues on forever in both directions, as sine and cosine curves do. And that's the x-axis, and we are totally done. So there's the graph of f of x, which is sine of 5x. Not bad, and has graphing within it, which I really dig. Speaking of problems that I dig, this is one of my favorite problems because it occurs throughout the rest of trigonometry. You're given a couple angles, A and B, and you're given trig ratios for them. So the cosine of A is a -5/13, and sine of B is 3/5. You're also told what quadrants those angles terminate within. So if I were to draw these out, which I highly recommend you do, you have in quadrant 2, the angle A terminates. So that's actually the angle A right there, but I'm going to use a hat here just to say that that's my reference angle. And you know the cosine of the angle A is a -5/13. That is, the adjacent side to the reference angle is -5, and the hypotenuse is 13. And you can go ahead and use Pythagorean theorem to find out this is 12. Because you're in quadrant 2, it's a positive 12. The y values are positive in quadrant 2. That's the significance of using this quadrant. Angle B is in quadrant 1. That's kind of an easy one. And we have a right triangle that we can draw there. And we're told that the sine, which is opposite over hypotenuse, is 3/5. And again, using Pythagorean theorem and the quadrant, you find that the adjacent side is a +4. Great. And now we're asked to find sine of A minus B, cosine of A minus B, and tangent of A minus B. We don't even know what A is. We don't even know what B is. And we definitely don't know what A minus B is. However, we can do all of this. So sine of A minus B, according to the sum and difference identities, is sine of A cos of B minus, because remember the sine keeps its sign, sine of B cos of A. And all I need to do is read from my triangles. Notice here's my triangle for A, and there's my triangle for B. I'm just going to read off of these triangles to find the ratios. For example, the sine of A, opposite over hypotenuse, is 12/13. So this is equal to 12/13. Times the cosine of B is adjacent over hypotenuse, 4/5, minus the sine of B is opposite over hypotenuse. Did not mean to erase that, but there we go. Opposite over hypotenuse, 3/5. And the cosine of A is adjacent over hypotenuse. So that's going to be -5, so times -5 over what is that, 13? There's no point in me canceling denominators here because I want to glue these together as a single fraction. So I have 48, let's see, that's going to be plus 15, all over 50 plus 15, 65. And that will simplify down to 48, 58, 63 65ths. So even though I do not know what a minus b is, the angle, I can still find the sine of it. That's kind of interesting. Now again, that was part A. Part B is asking for cosine of the angle A minus the angle B. And again, sum and difference formulas. That would be cosine of A, cosine of B, plus, again, cosine doesn't like its SIGN sign, so it's going to switch it. Sine of A, sine of B. And again, I just go to my triangles. I actually have all the numbers written up above, but I would go to my triangles and say, oh yeah, so in my triangles, cosine of A is negative 5/13, cosine of B is 4/5, plus sine of A is 12/13, and sine of B is 3/5. If you're wondering how I got that so quickly, I actually was just looking at these values right there. And again, they have the same denominators, so you can add them up. That's negative 20 plus 36 all over 65. And what is that? Positive 16 65ths. There you go. That's the cosine of A minus B. Finally, the tangent. And this is the one where I told you I don't require my students to memorize this one, because you can always use the fact that you know the tangent of A minus B is the sine of A minus B over the cosine of A minus B. Very powerful ratio identity. The sine is 63 over 65. We just computed that. And the cosine is 16 over 65. Again, we just computed that. Multiply numerator and denominator by 65, and you get 63/16. There you have it. Very nice. So that's a good, solid problem. One of my favorites, because this problem gets carried through to all the other second level or second tier identities. Now here we're presented with a tangent one without sines or cosines. Now what are you going to do? Well, in this case, you're going to have to use the formula for tangent of A plus B. We're told that the tangent of A plus B is equal to 3. The tangent of B is 1/2, and we need to find the tangent of A. I'll just remind you, and I will also say that I don't have this memorized. It's just that I remember it right now because I just did it a moment ago. Tangent of A plus B is the tangent of A plus the tangent of B being divided by, I'll zoom in here, 1 minus the tangent of A, tangent of B. But we were told that the tangent of A plus B is 3. So this tells us that 3 is equal to tangent of A plus tangent of B. But tangent of B, we were told, is 1/2. So I'll just trade out that tangent of B for 1/2 over 1 minus the tangent of A times tangent of B, which again, we were told is 1/2. And we need to find out what tangent of A is. My first move would be to multiply both numerator and denominator of this compound fraction here by 2. It's just a habit of mine, so I'm going to go ahead and do that. This will imply that 3 is equal to 2 tangent of A plus 1 all over 2 minus tangent of A. That's just distributing that 2 through. Next thing I'm going to do is get rid of fractions by multiplying both sides by 2 minus tangent of A. So this will give me 6 minus 3 tangent of A is equal to 2 tangent of A. That's supposed to be an A, plus 1. So again, all I did there was multiply both sides by 2 minus the tangent of A. Good elementary algebra, quick multiplication. Now what I'm going to do is move everything that has a tangent of A to one side and everything without to the other. So I'll add 3 tangent of A to both sides, and I'll subtract 1 from both sides. And this will give us 5 is equal to 5 tangent of A, or in other words, tangent of A is equal to 1. Notice they did not ask me what is A, they asked me what's the tangent of A. There are actually an infinite number of answers for what A is. It could be pi over 4, it could be 5 pi over 4, it could be any multiple of pi, any integer multiple of pi away from pi over 4. So I cannot tell you what A is, but I could definitely tell you what tangent of A is. Really good problem. Now there are two ways to consider this style of problem or go about this style of problem. The way that I'm going to do it right now only works if you have special ratios, which we do. It's critical that you remember inverse trig functions return angles. And the angles they return are incredibly restricted. So both of these return different angles, and those angles are highly limited. So I'm going to say where cosine of theta 1 is equal to a half, and more importantly, theta 1 is between, well, let's think about what we're dealing with. We're dealing with the cosine inverse. Cosine inverse returns angles between 0 and pi. Very important that you make that note. Same thing about this cosine inverse of 1 equaling a theta sub 2. That is where cosine of theta sub 2 is equal to 1. Again, I just want to make a mention. Cosine inverse only returns angles between 0 and pi. Now, normally, you would not be able to do this because if it was, for example, my students, they wouldn't be handed special ratios. But I do want to showcase what you could do if you were given special ratios like this. If you take a look at the cosine here is positive, and of the two quadrants that the cosine inverse will return into, which are quadrants 1 and 2, which of those two quadrants will cosine be positive in? Well, it'll be positive in quadrant 1. So I happen to know theta 1 is actually a quadrant 1 angle. Not only that, but I've seen this ratio 1/2 before. If I draw out my special triangle, my pi over 6, pi over 3 right angle triangle, 1, 2, root 3, the side or the angle adjacent to 1 with hypotenuse 2 is going to be pi over 3. So I'm in quadrant 1 and I have a reference angle of pi over 3, so my actual angle is pi over 3. So I happen to know that theta 1 is pi over 3. It's a quadrant 1 angle and it measures pi over 3 radians, so it's pi over 3. The other angle, well, this ratio 1 is an axial ratio or a quadrantal ratio for the sine or cosine. The only way you're really going to figure out what that is, I think, the best way, is to draw out the cosine. Remember, the cosine inverse will only return angles between 0 and pi. So I don't need to draw too much of the cosine, just enough to get to pi. Here's pi over 2, and so on and so forth. We're just wondering what angle would we plug in to get an output of 1. And notice that angle is 0. Angle 0 for the cosine gives me an output for the cosine of 1. So theta sub 2 is 0. So this sign of a difference of angles, you don't actually need to use a difference of angles. And this is, I stole this from the textbook that we use in my course at CRC, but I think it's a silly question. I have another question in line that's next in line that is much more realistic as to what students will see on exams. So I'm going to finish this out. I'm going to say, well, that's the sine of pi over 3 minus 0, or in other words, just the sine of pi over 3. And just by using my special triangle over here, sine of pi over 3 is root 3 over 2. So I'm just going to write this as root 3 over 2. I also should note, I've taught trig, pre-cal, calculus, all this for years, and one of the worst things you can do as you move forward, once you've taken trig, you do not want to stop right at a sine of pi over 3. It is assumed you know what that is, so evaluate it. If you don't evaluate it, it tells your instructor that you don't know trig. It would be as if you do all this crazy good mathematics and you leave your answer as 1 plus 2 or something like that. Well, you've taken arithmetic, finish your addition. Just like you've taken trig, or you're in the middle of it, when you're done with this course, or as of right now, you should evaluate that. Never leave it as a sine of a special angle or cosine of a special angle. Actually evaluate that. The very last example is the one, like I said, I tend to put on exams. This style of example right here. So if you're one of my students, listen up. If you're not one of my students, still listen up, because likely your instructor does the same thing to you. So here we have a cosine of a tan inverse plus a secant inverse. Don't get overwhelmed by this. The whole trick to doing mathematics appropriately is to take your time and simplify the symbols. So tangent inverse, just like all inverse trig functions, just returns an angle. And secant inverse, just like all inverse trig functions, just returns an angle. The tangent inverse, actually, it returns an angle between negative pi over 2 and positive pi over 2. That's the angle restriction on the inverse tangent. If you don't remember that, you should go back, watch the videos on the inverse trigonometric functions. I derive all this stuff there. The secant inverse is a strange one. It's one of the oddest inverse trig functions. I just decided to do it here, but the secant inverse is defined to return angles between 0 and pi over 2, and I should say and here, pi and 3 pi over 2. Don't worry too much about those edge points. I include the left edge, I don't include the right edge. Don't worry too much about that. That's not going to come into play here. So again, I'm simplifying the notation. I'm just saying, listen, this is not the cosine of a tan inverse plus secant inverse. Let's not write it that way. Let's write it as the cosine of theta 1 plus theta 2. Notice how clean that is. Now, I do want to mention something about theta 1. I'll say where tangent of theta 1 is equal to a negative 7 over 5. 5. That was supposed to be a 5. I don't know why I wrote a 2. Now, this is a negative number. Theta 1 will be either quadrants 4, it will either land in quadrant 4 or quadrant 1. Of those two quadrants, where's the tangent? Negative. If you said quadrant 4, you would have been absolutely correct. Tangent is negative in quadrant 4. So I know that this tangent is in the angle theta 1, which I didn't label, but theta 1, is in quadrant 4. Now in these problems, it's best to draw it. So here is my theta 1 terminating in quadrant 4. I happen to know that the opposite of that angle theta 1 over the over the adjacent is going to be a negative 7 over 5. We have to just decide which of those two is the negative side, but it should be somewhat obvious. The x value is positive in quadrant 1, but the y value, in quadrant 4, but the y value is negative. So there we go. That's how we get the negative 7 over 5. Now, if I go ahead and take a look at the next restriction, or the next angle, secant inverse returns an angle theta sub 2, where secant of theta sub 2 is equal to a negative 3 halves. Well, of these two quadrants where theta 2 could land, quadrants 1 and quadrant 3, of those two, where is the secant going to be negative? If you said quadrant 3, you're absolutely correct. So I'm going to go ahead and draw my theta 2 into quadrant 3, just so we can see it. Oops, except I need to use an actual pen. So we have an angle opening into quadrant 3. I'm going to, even though this angle right here is not theta 2, it's actually the reference angle for theta 2, I'm still going to call it theta 2. And I'm just redrawing it because it was kind of blocky. And we know that secant is hypotenuse over adjacent. Hypotenuse over adjacent. One of them has to be negative. And I mentioned it in a previous video, but I'll say it here again. Hypotenuse are never negative. So it must be the adjacent, and that totally makes sense because the x value is negative in quadrant 3. Now that I've drawn all that, I can continue with the problem. I'll grab this guy, move it here, so we have the cosine of theta 1 plus theta 2. The sum of angles formula for the cosine is cosine of theta 1, cosine of theta 2. Cosine does not keep its sign, so it's going to be minus sine of theta 1, sine of theta 2. So if I have triangles drawn for theta 1 and theta 2, I can just steal the information from those triangles to fill out what's the cosine of theta 1, what's the cosine of theta 2, what's the sine of theta 1, what's the sine of theta 2. So let's go ahead and look at this first one, cosine of theta 1. Well, cosine, here's theta 1 right here, cosine's adjacent over hypotenuse. Well, this tells me I have to find the hypotenuse, but that's just a little Pythagorean theorem problem. 49 plus 25 is 74, so this is a square root of 74. Remember, hypotenuse are always positive. So let's see, cosine of theta 1 is 5 over root 74. 5 over the square root of 74 times. Now the cosine of theta sub 2, well, that's here. And that's just adjacent over hypotenuse, which is negative 2 over 3. Negative 2 over 3. And then minus sine of theta 1. Going back over here to theta 1. The sine is opposite over hypotenuse. Negative 7 over root 74. So negative 7 over root 74 times sine of theta sub 2. Sine of theta sub 2 requires me to have the opposite over hypotenuse. Well, that's just going to be a quick Pythagorean theorem problem. You'll find out that that's root 5. However, we're in quadrant 3, so that's a negative root 5 because our y values are negative in quadrant 3. So the sine of theta 2 is going to be a negative root 5 over 3. Let's go ahead and write that down. Negative square root of 5 over 3. And now notice they have the same denominators. You can just add them up nice and cleanly. You have a negative 10. Let's see, 3 negatives multiplying is a negative. So minus 7 root 5 all over 3 root 74. And I wouldn't bother really cleaning that up. 35, 36, 37. Yeah, I wouldn't bother cleaning that up. I think that that is a well-written answer for the cosine of theta 1 plus theta 2. Or in other words, that is actually the cosine of the tangent inverse of a negative 7/5 plus the secant inverse of a negative 3/2. That is a really solid exam level problem. So doing these, you can just make up your own all day long. These are not terrible to make up. Just make sure that whatever inverse trig function you're using, that the ratio inside that inverse trig function works. So you don't want to, for example, do a secant inverse of a half because secant will never become a half. You need a number greater than or equal to 1 in magnitude. So anyhow, but you can make these up all day long. They're actually not hard to make up. They're just a little bit of work to solve. Anyhow, so that's it for this video. We're done kind of playing with expressions involving the sum and difference formulas. In the next video, we're going to do some proofs.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Brings for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.